Good morning, good afternoon, wherever you are in the world. Welcome to the Demonstrating Electric Driveline Design Process Using a Case Study webinar. Thank you for joining. I'm Rahini Sile, Romex Marketing Campaign Manager, and our presenter today is Barry James, Chief Technical Officer and Head of R&D at Romex Technology. I'll now hand over to Barry and let him give a full overview webinar.
Hello to all of you. So today what I'll do is I'll take you through various aspects of this project. The project was ODIN, which stands for Optimized Drivetrain by Integration, Optimized Electric Drivetrain by Integration. We'll talk about the targets of what it was designed to achieve when we first kicked off the project, and also about how the consortium was selected and set up. We'll talk about the design challenges that were faced in the first parts of this project and how we actually took those design decisions in order to come up with a design. And then we're actually going to look at some lessons learned from the design and also from the testing that's been carried out to date on the gearbox and the driveline, which was completed in the first loop. We'll have a project update to see where we are at the moment, and then we'll summarize with regard to how the project is done. The initial targets for ODIN was set in 2011, and it's worth going back to that time to see what were the pressures at that particular time. The focus was on a subcompact or compact electric vehicle with a peak power of around 65 kilowatts for 30 seconds. And yes, the target was to have a highly integrated electric machine, power electronics and gearbox into a single shared housing. There was an aim to have a fairly high-speed motor. Certainly that was one of the initial targets. We could see that over time, as we've done electric vehicle projects, a lot of the motors have got higher and higher speeds. And so being an R&D project, the aim was to really push this to a much higher speed to see what problems there might be, can we overcome them? Being R&D, you're getting public money, and it was very much a case of we shouldn't just be another Me Too design. We shouldn't be similar to what was already out in the marketplace. We were tasked with having a cost reduction, having a cheap design. The initial target was thought to be up to 50% cost reduction compared to reference powertrains. And also at the time, we were tasked with the idea of avoiding rare earth metals. The graph that you see there is a plot which is being commonly discussed. It is the cost of rare earth metals, which going through 2011, prior to the setup of the project, had seen a price spike. And so this was looked quite frightening at the time, and so the change to non-rare earth metals was very much desirable. And in setting up the project, we then thought, okay, a switch reluctance motor is a design which hasn't really been used that much, certainly not in terms of the main propulsion system, but it is worth investigating that to see whether that can be used. The work that Romex had done prior to that, we had been busy for a number of years in doing work on electric and hybrid vehicles, and as you can see, the work we've done on ODIN has led to many other projects because we gain a lot of experience. In actual fact, you can see here, this is the ODIN project along here, and you can see that that's one of many projects that Romex has carried out during that particular time frame. But you can see before the consortium was selected, we'd had a reasonable experience in electric and hybrid vehicles, and this was used because we've been working with some of the consortium partners previously. We were invited in to join the consortium in order to carry out our work. We said that switch reluctance motors was one of the key items we were looking at. Now we know that switch reluctance motors have a very high dynamic content in terms of torque ripple, and so our experience on dynamic simulation was one of the reasons why we were brought into the consortium. We also have ICEA from Aachen University, who were experienced in the design and simulation of switch reluctance motors, especially with regard to innovative control systems. And then the consortium was led by Bosch, including GKN Driveline for the design and manufacture of the gearbox, SEAR Automotive for the manufacture of the housing, Fuchs for the design of the oil and supply of the oil, and then Renault was for the vehicle integration and setting the vehicle targets. The demonstrator vehicle is the Renault Zoe, and that's the application for which the driveline is being designed. And then the consortium was put together and the project was kicked off in September 2012. So as we went through the initial parts of the project, we came across common challenges which are, I guess, are common to all electric vehicle designs. What's the best layout? How many gear stages should we have? What's the overall ratio of the gearbox? And that will affect the overall maximum speed of the motor, because at the vehicle maximum speed, the rotational speed of the differential, I guess, is fixed. And so if you increase the overall ratio of the gearbox, then the motor can be smaller and more compact. We wanted to make sure that the driveline will be efficient. Obviously, that's one of the key requirements of an electric vehicle, but also not just how efficient it will be, but how do we make it more efficient. We wanted to have an integrated system for high power density, but as we increase the power density, then we have a problem of cooling. But is there an option of integrating the cooling of the motor and the gearbox in order to make the system smaller and also to take some of the heat out of the motor and use it in the gearbox? And also, can we design for low noise? Is it possible to predict the noise? Is it possible to make sure that we have a low noise condition? So those were the challenges which we kicked off. In looking at the gearbox and the impact of the gearbox on the motor, we carried out some initial considerations. GKN and Romax were discussing this in the early parts of the design process, and we came up with some ideas. The obvious ones are simply single-speed gearboxes with maybe 2 stages, maybe 3 stages. There are actually some other ones. We can look at maybe two speed options. So 2 SP means 2 speed options. We could look at 3 speed options. Maybe we could look at having 2 motors. Some of those ideas were being expressed as possible designs. And of course, in a design process, it's difficult to really simulate all of these and really do a quantitative assessment to see which is the best design. So at this particular stage, a lot of them were really qualitative. We were able to compare each of these layouts and each of these options really to see what did we think was the best design with regard to a series of design requirements and a series of design options. Different layouts here also express P means parallel, E means epicyclic, because we could have 3 stages which are parallel, parallel, parallel gears, or parallel, epicyclic, parallel, for instance. So we have a number of different options which we can study, and in looking at these we really did come back to the decision that we were looking at a compact vehicle, city driving vehicle, and cost was of consideration. So really there wasn't a huge benefit in going to multiple speed gearboxes, and so it did bring us down to a single speed gearbox. And since we could fit 2 external gear stages into the packaging space, we felt that that would be cheaper for manufacturing than a planetary gear set. And since we could still get a decent high-speed motor with 2 stages, we decided to go for 2 stages. So a simple single-speed gearbox with 2 stages seemed to be satisfactory for this particular application. Really no need, no benefit in making it more complicated than that. But it would still give us a decent amount of innovation, because of course we'd still go for the integrated cooling, we'd still go for the high-speed motor, we'd still go for the design for low noise. Having selected that, there's still a little bit of uncertainty. Okay, we knew we wanted to go to high speed, a high overall ratio, and this would achieve a smaller, lighter, cheaper electrical machine. Okay, it would mean that there'd be a higher overall ratio for the gearbox, but there is still some uncertainty at this particular time. At Romax, we'd done a large number of projects, and we had done efficiency improvement projects for gearboxes for electric vehicles, And we've got a lot of test data where we validated our simulation against test data for the efficiency of gearboxes. But these were at conventional speeds, much lower input shaft speeds than we were considering here. And we didn't really have any test data to show that we could validate against test data for the high speeds which we were looking at here. Indeed, we discovered at the start of a project that there wasn't really much, it was difficult to find test facilities to run at these particular speeds. Also, we weren't really able to do that much simulation of these, of the overall driveline efficiency at these high speeds. At Romax, we could design gearboxes in Romax Designer and simulate the efficiency very quickly, in a matter of minutes. We could get the efficiency maps very quickly. But the corresponding efficiency calculations for motors using 3D finite element analysis took days, if not, best part of a week to do an efficiency map. So it was very difficult to actually come up with a driveline efficiency model which was providing results in the timescale that was suitable for the design. At this stage, we really did say, okay, we don't really have the data that's available to us in order to make a quantitative decision on what is the best ratio. But we came back to the original brief of the project. R&D cannot be a me too design process. A project needs to set a challenge even if there's a risk of failure. And so we did set a high speed as a target. High-speed electric motor, a switch reluctance motor at 22,500 RPM. We knew this was going to set some challenges for the project, but that is what R&D is about, and that is why we, as setting a target, we risk a problem, but we also are able to start to develop something special as well. So, in order to mitigate those high speeds, we would bring in MVH simulation in the early parts of the development process. Romax was able to offer that. And we're also looking at high degrees of integration with regard to cooling and lubrication. Arkin University were to develop optimized design and control of the switch reluctance motor. And from the power electronics, we would have high switching frequency and highly dynamic current sensing. We would aim for a high efficiency gearbox, which was going to be dry sump in order to overcome some of the problems with lubrication and high speed. And we were going to maximize the overall ratio with regard to what was possible for 2 stages. Of course, the MVH would be optimized for this particular design, and we would also look at any synergies that we could achieve with integration between the power electronics, the motor and the gearbox. So as we went through the design process, we had the challenge of designing the cooling. So the thermal simulation of this particular design was carried out by Romax Designer, where we started off doing 1D system level models of the layouts to see how can we design the cooling of the system, how can we look at what options can be used in terms of cooling the motor and bringing that heat into the gearbox. The purpose of this integrated cooling was that as we were taking heat out of the motor, we could heat up the lubricant in the gearbox more rapidly, in which case, under startup conditions, the efficiency of the gearbox would increase more rapidly and the overall drive cycle efficiency would be better. So you could see the way that the non-integrated cooling, non-integrated temperature rise could be assisted by having an integrated cooling. And also the temperature of the motor is also reduced as well. Okay, this is also integrated with the idea of a dry sump topology, which is enabled to us to look at the best cooling circuit and also in order to design the gearbox for greatest efficiency. We also had to consider, cooling the power electronics as well, because they require consistency of temperature for the best reliability. The design of the lubricant was also carried out in this stage. We see that in the design and operation of an electric vehicle, we have a range of different operating conditions. from high load, low speed conditions to low load, high speed conditions. And this gives us different challenges for lubrication. Of course, in all of these conditions, we can simulate using Romax Designer what the tooth contact is and what the sliding velocity is at each part of the tooth. And this data, we were able to supply that to Fuchs in order for them to actually start to develop the lubricant. So they were able to develop lubricants. They can carry out some mini traction machine tests. This can feed through into, and they also had FZG tests for scuffing and load durability, and we can replicate that in Romax. And that enabled us to actually look at the lubricant and its effect on the efficiency of the gear mesh, not just in terms of the viscosity of the oil, but also in terms of the additive pack as well. So when we were looking at this, one of the guys from Bosch came up with a good phrase saying that we were designing the oil for the machine and the machine for the oil, which is quite an accurate representation of what we were doing. We were supplying Bosch with data on how the teeth come into contact and what the surface roughness is, and Bosch was supplying us with data on how the lubricant was reacting to that, what the lubricant performance was, and we were able to quantify that in terms of the overall efficiency improvement. This particular aspect can be demonstrated in the effect on the lubricant efficiency in Romax Designer. So if you take two IE lubricants with identical viscosities and you put them into a standard ISO calculation, you come out with an identical efficiency. Now, in reality, that's not the case because the efficiency of the gear mesh depends not just on the viscosity of the oil, but on the additive pack and friction modifiers. And the FVA 345 method, which we've implemented in Romax, allows us to identify that, and this way we can differentiate between different oils in terms of their effect on the efficiency. And you can see that in certain instances the impact can be quite noticeable, and this obviously depends on the operating condition. As I said, one of the concerns we had within the project was how to design something that is quiet, so we had to design something that's good for low noise. We're very familiar with the process of designing something and developing something, and many times when we've come to solve noise problems, we are involved at the end when someone has designed something, they're testing it, they assemble it, and they've got a noise problem. And of course we can simulate things, we can validate against test data, and we've done this many times. The trouble is that at this stage it's all a bit late. There's going to be someone with a Gantt chart who's saying, sorry guys, it's too late, we've got to implement this design, there is a vehicle release date. What we really need to do is see what we can do in terms of designing something for noise not at the end of the design process, but earlier in the design process, when you can actually carry out rapid design, analysis, redesign iterations, where you're designing the housing, and maybe even before that, when you don't actually have a housing. So that's what we set off to do in this particular project. At the concept stage, we have no housing, so we cannot predict the radiated noise, but what we can calculate is the sound power coming through the bearings. And we're not predicting how noisy it's going to be, but we can assess one design against another, and by selecting the quietest design, then we give the design a best possible chance of being quiet at the end of the design process. In doing so, we had to check that our method was correct. If you calculate the vibratory power going through the bearings of a simple design with no housing, you actually get a result of a total power which is very different from what you get out of a full model with a complete housing. But what we managed to do is we managed to develop a simplified representation of the housing which we could apply at concept stage, and we've discovered that the results are very similar. So this sort of representation of a model which we can do at concept stage is sufficient because we get more or less of a right result, and also the shape of the vibration in terms across the frequency range is accurate. So that allows us to use that sort of model and that sort of assessment right at the very early stages of the design process to assess which was the quietest layout. The next stage of doing that was to actually build up a housing. Of course, we didn't want to wait to have a fully detailed housing in order to make some recommendations. So GKN created an outline design which wrapped around the housing, and we were able to use the mounts. Okay, these are the mounts, and there's a mount stiffness onto the housing in order to get the overall behavior of this structure from a dynamic point of view. We were able to simulate this system with regard to motor noise, motor excitation, and also transmission error. And you can actually see the peaks. These are peaks to unit excitation. So this is the conditions at which the dynamic response of the system is at its worst. So regardless of what your transmission error is, we could predict that there's going to be a peak at this particular value, and we can do something about it. So we're reducing the noise, not just in terms of reducing the excitation by designing good gears, but reducing the dynamic response. And so we could see there was a peak due to motor noise. This sort of breathing mode at 13,000 RPM was because we had no ribs on the end of the motor, and we could feed that back to the design team in order to put ribs there. And they were able to take that into account, implement this in the design that they were carrying out. And then when we looked at the simulation, then of course that leads to a reduction in vibration here. We could also carry out the simulation of to other electromagnetic forces, such as this 6-mode excitation, and we could see that we have substantial reductions in the noise arising as a result of this. We also got reductions due to the radial forces, okay, so 13 dB reduction here, and we were able to reduce due to, okay, there's a radial force and also transmission error as well. That sort of reduction there indicated a substantial reduction in the response due to transmission error. So that indicated that the design for low noise was successful, not just in designing quiet gears, but also designing for a low system response. We spoke earlier on about how we would design for the lubricant and its effect on efficiency, and a number of lubricants were tested. So we can see here, we're not able to share the details of these lubricants with you, but we can show that they did actually have a substantial effect on the efficiency of the gearbox. So this allowed us to close the loop. We were able to show that designing the oil for the machine and the machine for the oil had been successful because the lubricants that we predicted as being efficient were actually efficient when we tested the entire gearbox together. And this was successful not just for the gearbox on its own in terms of good lubricants, but also for the actual performance of the gearbox itself. The Odin gearbox was compared against testing of a baseline gearbox. This is a current production EV gearbox from another alternative manufacturer that we took out of a vehicle. And across the speed and load range, then it showed that the Odin gearbox that we had designed had better efficiency. So that showed a success. So we did actually have other tests. The gearbox design was successful. We did run some MVH testing, but at this stage the model setup was, the boundary conditions were very different from the simulation which we'd done originally. Obviously the first simulation we'd done had been with the vehicle boundary conditions, and the actual MVH test was very different. And at this stage the project had moved on because unfortunately the switch reluctance motor had been tested at that particular time and did not meet the efficiency targets. This was despite the novel control strategy that had been developed. Also at that particular time, the loop 1, at the end of loop 1 as we called it, the price of rare earth metals was less of a problem. If you recall right at the start, the peak in 2011 had been followed by a reduction in the price in subsequent years. The economic justification for switch reluctance motors had reduced. So as a result of that, the loop 2, which was always planned, we decided to go for an induction motor based on a design that Bosch already had, but with a similar gearbox to loop 1. So the project was extended by a year and a slightly different technical route was taken. If we look at the lessons learned, we see that the design of integrated electromechanical drivelines brings new uncertainties in doing this work. So there's some things we don't know. We don't have a long period of experience of designing these systems in the same way that we do for, say, manual transmissions. It's difficult to develop a new simulation process as well as doing a new design. So if you want to innovate in the design, it's difficult to innovate on your simulation process at the same stage. One of the guys at Renault came up with this phrase of technological building blocks. And so it is important that these are in place before you start your design, as opposed to trying to develop them at the same time. On the other hand, we did find that we were able to use upfront simulation, such as we did in MVH, and that was able to provide great benefits within the project. It did also show that close collaboration between the motor and gearbox design activities are important, because there were times where it needs to be clarified who owned which component and which design parameter was being chosen between Bosch and GKN. Remember, when you've got an integrated electric driveline with integrated motor and gearbox, we have a single shaft which supports the rotor of a motor and also the first input gear pinion. And despite all of this technical work, of course, we have to accept that engineering decisions are still subject to economic influences. So, as a summary, update of a project, the motor has been changed to an induction motor, which is supplied by Bosch. The maximum speed is now 15,500 RPM. So the overall ratio had to be changed, which meant we had to design new gears. But the gearbox design process that we used in loop 1 was replicated to make use of the successes that we had for efficiency and lubricant design. Also, the methods for designing for low noise, thermal performance in an integrated system were carried over. The tests of these have just started in the last couple of weeks. We haven't got any data at the moment that we can share with you, but we will certainly be looking to disseminate that worldwide when it does become available and when this project does conclude. So, as a summary, Romex has had at first hand, very detailed involvement in the design of a full electric vehicle project with cross-industry collaboration involving the motor, gearbox and vehicle together. It has actually kicked off a large amount of R&D work, which is based on the limitations of what we saw as the state-of-the-art in the design and understanding of electric vehicle drivetrains. And so this has allowed us to develop further methods which have moved our capability on further. And very much this is surrounded the understanding of the interactions between the electrical system and the mechanical system. And this is essential for the design success. So that really has become part of what it was the drivers for the electric machine modeler, which is part of the the latest release of the software, where we take the excitations of the motor and put that into the simulation of the combined system for the gearbox and motor. I think that was demonstrated in the previous webinar, the last one, and also I think the next webinar explains a little bit more about how the excitation from the electric motor can be simulated. So that is the end of my webinar. I think we'll go on to questions and answers now. Okay, so there's one question which is why did you choose an induction motor because of a reduction in rare earth price? If that was the reason, you should have gone for a brushless DC or AC. Induction motors don't have any permanent magnets. which is correct. But part of the reason was also, well, switch reluctance motor failed itself because of the efficiency. It didn't meet the efficiency targets. So that was the main reason for discounting it. And the project wanted to move on. I think it was just partly that Bosch had an induction motor which was available at the time that had been designed and could be modified in order to be applied to this project. So I think that was the main reason. So I hope that's answered that question, but we could continue that. The next question which was asked was, are there different ratios for a switch reluctance machine as opposed to in induction motors? Well, again, in the switch reluctance motor, we chose the overall ratio in order for it to be as high as possible because we wanted to set our challenge of having a high speed machine. When it came to the induction motor, then we came up with the 15,500 RPM was because that was the speed of the existing machine. So the difference in the overall ratios was not necessarily related to the different machine types. It would be very interesting to be able to do that study to actually check what would be the different overall ratios depending on the machine types. Okay, you showed a slide of matrix of overall ratio versus second stage ratio. Well, what was the reason the overall ratio versus first stage ratio was not shown? Well, the reason for that is once you've selected the second stage ratio, the first stage ratio is automatically selected. So they are interdependent. In actual fact, this red line is because for when you go to a high overall ratio, if you make the second stage ratio too small, the first stage ratio becomes too large, and so some of these options, some of these design options down here, some of these design options in this design space become disqualified. And there's one final question, which is, does the process work for wet sump in terms of designing for efficiency? So we've had the design for the efficiency and design for the lubricant. So this process works for both wet sump and dry sump designs. We assume that the lubricant gets into the gear mesh and that the viscosity and the additive pack of the lubricant acts on the gear mesh in order to give a certain efficiency. And this process can be works whether the oil is splashed or whether it is sprayed with a dry sump. So this works whether it's dry sump or wet sump. Okay, so I think that's all the questions. I think that's all we've had so far.
Thank you very much, Barry, and thank you to those that have sent your questions through. If you do have any questions, we will answer them via email. So not to worry if you've not thought of any questions at this moment. So I just want to remind you all that you can send your emails to marketing@romaxtech.com, and we will email the answers across to you as soon as possible. We've got our Romax Global Forums this year. You can join us on them, and we will be covering electromechanical technology integration in more detail. You can see the latest simulation developments and new capability of how simulation tools are being developed to simulate and reduce noise from electric and hybrid vehicles. We've got the EU forum, so anyone in the EU, please come along if you can. There's still time to register on the 27th and 28th of September at Frankfurt, Germany. The China forum is in October on the 18th in Beijing, China, and we've got the Korea forum in Seoul in South Korea on the 20th of October. If you'd like further information on what the agenda will be and also how to register, please visit romaxtech.com events Global Forums 2016. So we hope you will join one of our future webinars. We will also be sending e-shots with information on our webinars. We constantly promote them. So we have got another webinar coming up at the end of October, and we'll also be having some more electrification webinars in November. We hope you'll be joining one of our future sessions. Thank you and goodbye.